Okay, the last section we're going to look at for this week is 3.2, and it covers 3 topics: continuity, intermediate value, and end behavior. So, and this is actually for older graphing calculators. Most older graphing calculators assume that everything you want to draw should be connected, right? Meaning that if you were tracing it, you'd never lift up what you're using to trace it. There's no breaks or holes in the graph. So if I graph something like this, is there any value that I'm not allowed to plug in for x? Is that 3? And if I basically turn this calculator into an older calculator by turning off that feature, detect asymptotes, the calculator is going to try to draw this connected. Well, we know it shouldn't be, because when you get to 3, something weird happens. So the calculator doesn't really know what to do. Right? It tries to draw something, but it's not really sure what's happening. On a newer calculator, it knows that there are certain values that you can't use sometimes, and it accounts for that correctly, drawing the graph like that. That's what it should look like. There should not be a connection between each part. All right. So this is a graph that if you were actually drawing it, you would draw the first part, you'd lift up your pencil, and then draw the second part. Okay. It's not a connected graph. And your calculators are all set to automatically detect things like that, okay, if you're using one of mine. So that's basically what I just graphed. Could you trace the graph that I just drew without lifting your pencil? No. Let's graph this one. I don't know if you've ever seen this one before. But could you trace this graph without lifting your pencil? No. That one you'd have to lift your pencil even more times. Right? But the point is, you can't trace it without lifting your pencil. Now, how about this? This is a parabola. Could you trace that one if I drew it? You could, yes. So a couple of these graphs you could trace, one of them you couldn't, and that idea is called continuous or discontinuous. So we say that a graph is continuous from a starting point to a stopping point, some interval, if you can trace between the starting point and the stopping point without ever lifting your pencil. That's the simple way to explain it. Okay, so a graph is continuous on an interval if you have a starting point and a stopping point, A and B, and you can trace between those two starting and stopping points without lifting your pencil. If a graph isn't continuous, then we just say it is discontinuous. And there's all kinds of graphs that are discontinuous. I showed you 2 so far today. Usually if you have a graph where it would cause you to divide by 0, that's a place, that's what we call a discontinuity. It's a place where you would have to pick up your pencil and continue drawing somewhere else. Now, the other graph that looked like steps, I'm not really going to get into explaining it too much, but you could see that you'd have to pick up your pencil to draw steps like that. Okay, so any questions on that idea of continuous versus discontinuous? And I say without lifting your pencil, I mean your writing utensil, whatever you're actually using. All right, so when I give you guys a graph, you might be able to find some sections of the graph that are continuous, but then other sections are not. So we're going to look at this graph right here, the graph of 1 over x. Let's type that in first. First of all, when I graph that, is there any value you are not allowed to use for x?
0.
You can't use 0, so something weird is going to happen at 0. and you can see what happens. Now, technically, the calculator isn't even drawing that exactly the way it should be. Those blue curves should continue on forever in all directions. Right? Up, down, left, and right. So it really should look more like that one continues up, that one continues down. But the thing is, it never touches the axes. It gets closer and closer. It looks like it touches it because my pen, I don't have a pen that's infinitely thin. So when I draw, it has a thickness to it, so it looks like it's touching it. Right, but it's the same with the resolution on the screen. Okay, but it never touches it. So I want to name two intervals on that graph that are continuous. Meaning, give me a starting point, give me a stopping point for x values that I could trace between it and never have to lift my pencil. So could someone give me an interval here that is continuous? Yeah.
0 to infinity.
What did we say about 0?
Oh, well, like, you can't go on 0, so.
Okay, so go ahead.
Parenthesis, 0, infinity.
Yeah, technically that is a continuous interval. Could you ever trace to infinity? No. But if you could, you'd never have to lift your pencil to do it. So that's continuous. Another continuous interval is from -3 to -1. That's from here to there, between those two dots. I could trace from there to there without lifting my pencil. Now, technically I could put a bracket on -3 because I could include it if I wanted to. I don't have to include it. There's millions of answers here. -10 to -9, -9 to -7.3, 2 to 5. Anywhere that you can start and stop without lifting your pencil is a continuous interval. Now, could someone give me an interval that is discontinuous? Meaning you give me a starting and a stopping point, and I can't get from your starting to stopping point without lifting my pencil on this graph. Yep.
-1 to 1.
Yep, -1 to 1. Basically, any interval that crosses what number?
0.
0. Yep. Here's another interval. -2 to 16. You can't go from a negative number to a positive number in this graph without lifting the pencil. Right, so you can find some sections that are continuous and some that are not. Any questions on that? Okay. I'm not worried about that one. Okay, so there's a couple different ways that you can have what's called a discontinuity. The first thing that can happen is you basically have a divide by 0. That's what this would be. You've got an undefined value. And this results, I don't know if you knew this as I was drawing it, but it's what's called a vertical asymptote. Has anybody heard of that before? Asymptotes?
Yeah.
So asymptotes, I showed you a feature on the calculator. You can turn off detect asymptotes. But basically an asymptote is just something that you get closer and closer and closer to, but you never actually reach it. So you have an undefined value, caused usually by dividing by 0, which results in a vertical asymptote. Another type of discontinuity you can have, besides a vertical asymptote, is a break. A break is what you saw in this step function. Looks like that. Now, we don't know a lot about this function, but I will tell you that the domain of this function is all real numbers. There are no undefined values in this function. None. You can plug in anything you want. But basically what this function is doing is it's rounding numbers off. So if you round a number to an integer, think about what happens. Do you ever get a decimal if you round an answer to the nearest integer? Emily? Do you ever get a decimal? No. If you're rounding to an integer, you'll never get a decimal. So that's why this function jumps. 1, 2, 3, 4. There's nothing in between 3 and 4. Right? Because this function basically just takes a number and rounds it off. Right? So you lose the decimal. All right. So is there any number that you are not allowed to round? Like if you tried to round this number, you'd get an error.
Negative square root.
Just sticking with real numbers. Is there any number that you're not allowed to round? What do you think, Chris?
0?
Sure, 0. Anything else? Jared, what do you think?
You hold numbers because they're already rounded.
Well, technically you can round a whole number because it would just be the same number. I mean, it's not even really rounding, but you could still. So is there, let's phrase it this way, is there any decimal number that you cannot round off? Yeah.
0.33.
I could round it, 0.3. Depends where you want me to round it, but I could round it, 0.3. Anyone think of a number? No, you can't. You can round any number you want. That's why the domain of this is all real numbers. Right? So this graph has what we call a break in it, just because of the way it rounds off numbers. Right? And let's look at this one. This graph has a hole in it. Let's graph it and see what it looks like. So it's x squared plus 3x plus 2. Okay, and it's divided by x plus 2. Okay, so this graph is going to have a hole. Okay, does everybody see the hole? Right there. You don't see it? No, I don't either. But there is a hole there. This is the trickiest one because you can't see it on the calculator. Where do you think there should be a hole? Look at the original formula.
0. Or negative 2.
Negative 2. If you go to the table and you type in negative 2, well, it's already there. It says error. So there is a hole there. There's no value at negative 2. But if you go negative 1.999, that's fine. And if you go 2.0001, that's fine. I'm sorry, I meant to go negative 2.0001. I just picked numbers extremely close to negative 2. Right? And if you pick a number extremely close to negative 2, it works. Just not negative 2. That's just showing negative 2 rounded, but it's really this. So it's like the hole is infinitely small. You can plug in negative 1.9999999. You can plug in negative 2.000001. That's why you can't see it, no matter how much you zoom in. You'll never see the hole. So how do you know there's a hole? Well, from the picture you don't. Okay? But factor what's in the top. What do you get if you factor what's in the top? Yeah.
X plus 1
Mm-hmm.
and x plus 2.
And what do you notice about what just happened? Anyone notice anything there?
X plus 2.
What's that?
You can cancel out x plus 2.
Yeah, what we have is a common factor in the top and in the bottom. Whenever you have a common factor, that's when you get a hole. That's the only way to tell. So as Elias just said, basically it's almost like the x plus 2's cancel out, and really what it's going to look like you're graphing is this, x plus 1. So watch what happens if I hit graph, because the blue graph, you'll see the blue one first. Now watch the red one. They look exactly the same, but they're not. The one in blue has a hole in it. The one in red does not. Okay? So the way I would graph it, if I had to do it by hand to show that there was a hole, do it like this. Make the hole bigger so you can see it. Okay, the calculator is not going to do that. It'd be nice if it did. But just put a circle where the hole should be. Right? So those are and that's a discontinuity, because if I was tracing this with my pencil, now I got to pick it up, put it down on the other side of the hole, and then keep going. Right? So discontinuities, you can have a divide by 0, which gives you an asymptote. That's no good. You can have a divide by 0, which gives you a hole, or you can have a break in the graph, okay, like in the step function. So, every polynomial is continuous everywhere. Like if you think of a parabola, I don't care where you tell me to put my pencil down on the parabola and where you tell me to pick it up. I can always trace from wherever you tell me to start, from wherever you tell me to stop. Always. Without lifting my pencil. If you can trace anywhere, no matter where you trace, and it's always continuous, that's called a continuous function. Okay, so a continuous function is a function that you can trace anywhere without lifting your pencil. Now, if I draw a picture of the first graph we had, it looks something like this. Kind of curved like this and like this. Is that graph in green a continuous function? What do you think, Karen? How come? Yeah, it's in two separate sections. There's a vertical asymptote at 0. Okay, so that is not a continuous function. Now, are there sections of it that are continuous? Yeah, you could find a small section, like from here to here, or from here to here, or here to here. There are sections that are continuous, but not everywhere. Not everything from negative infinity to infinity is continuous. Okay, so that is not a continuous function. Any question on that idea? So all polynomials are continuous functions. Parabolas, cubics, like the W-shaped one we did in the homework, you never have to lift your pencil to draw them. All right, so that's the idea of continuity. That's the first thing. And probably the hardest thing. So if you thought that was easy, then the rest of it will probably seem simpler. Okay, intermediate value property. First of all, this is a property that only applies to continuous functions. Okay, only applies to continuous functions. Okay. Here's an example of something that's continuous. Okay, I want you to think about this, and this idea that I'm going to tell you right now is basically explains this. So imagine that you had a cup of water sitting on the table at like 70 degrees, just like room temperature, okay? 70-degree water. And you heat that water all the way up to boiling. So it goes from 70 degrees up to 212 degrees. How many temperatures does it go through from 70 to 212? Yeah?
In whole numbers?
Even decimals.
Oh, infinite amount.
An infinite amount. It goes through every single possible temperature. So there is a time when the water is exactly 81 degrees. as it's heating up. There is a time when the water is exactly 97.6 degrees or 204.617 degrees. It might be a very short amount of time. But there's no way, as you heat water, that it can skip temperatures, because heating water is a continuous process from beginning to end. It doesn't skip anything in between. It hits all the intermediate values between the start and the stop. That's basically the idea of this property. All right? Versus, well, if you say, well, what's something that's not continuous? Me counting the number of people in this room. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did I count every single number from 1 to 10, including decimals? No, I skipped. I skipped everything between 2 and 3. I skipped 2.5. I skipped 2.4, 2.16. Right? That is not a continuous example. Right? So, the idea is if you have a function that is continuous over an interval, okay, A and B represent a start and a stop. So if you have a function that is continuous over an interval, then your function will be able to take on every y value between the starting y value and the ending y value. So basically you could have something like this. The coordinate of that point is a, comma, what's the y value? I don't know. F of a. Pretend like you had a formula for it. We don't have a formula. This coordinate is at b. What's the y value? I don't know, let's just call it f of b. You'd have some formula you'd plug b into and get the y value. When I drew from this dot to this dot, did I lift my marker? No. So that is continuous, which means you're going to hit every y value. Let's say this y value was down at 0, just making a number up, and this y value is up at 50. You're going to hit every single number from 0 on your way to 50 because you never lifted your pencil. You're going to hit 13. You're going to hit 12. You're going to hit 47.6. You're going to hit them all. Any question on that idea? Okay, only applies if it's continuous. All right, so let's look at an example. So f of x equals 3x minus 4. That's a polynomial. It's one of the simpler ones. If you draw this, what is the shape of it? Yeah, straight line. It's just a line. Just a line with a slope of 3 and a y-intercept of 4, negative 4. So there's no turns in it at all. Are lines continuous? Yeah, of course. You never lift your pencil when you're drawing a solid line. So I want to look at the interval from negative 10 to 10. This line goes on forever. I'm basically going to look at a small section of it, from negative 10 to positive 10. Well, when you're at negative 10, you're at some y value. We'll figure out what it is in a second. When you get to positive 10, you're at a different y value. The key is you're going to go through all the y values from here up to there. You're going to go through every single one of them eventually. My question is, will you go through 15? So what we really have to do is figure out where are we starting, where are we stopping, and is 15 somewhere in the middle? If we're starting at 20 and we're going to 30, then no. You're not going to go through 15. If you're starting at 5 and going to 50, then yeah, you'll go through 15. So we just got to figure out where we start and stop. So let's find the y value if we plug in negative 10. Okay, so I plugged in negative 10 for x. What's 3 times negative 10?
Negative 30.
Minus 4.
Maybe 34.
Okay, so we are starting at a value of, I don't want to circle it because that's not the answer, but we're starting at negative 34. We're going up to, well, let's see where this ends. Plug in 10 for x. What's 3 times positive 10? See it?
30.
30 minus 4?
26.
26. So I'm starting at negative 34. I'm ending at 26. Am I going to hit 15?
Yes.
Yes. Why?
Because 15 falls between those two numbers.
Yeah, 15 is in between negative 34 and 26. So you're going to hit 15 somewhere. Now the question is, where do you hit it? That's what C is. They want to know where. So where would I put in 15 in that formula to find out the x value that I plug in to get 15? Think about that 15. Is that an x value or is that a y value?
Why?
That's a y value. So where is the y in this equation? Yep, f of x. So you're going to fill in what I just underlined. You're going to fill in 15. 15 equals 3x minus 4. Solve for x. And that'll tell you the value that you can plug into this formula. And it will be between negative 10 and 10. We already figured that out. That answers the question. So we're going to get 19 thirds. Which 19 thirds, if you take 19 divided by 3, that's what, 6 and a third?
6 and 2. Oh yeah, 1/3.
6 and 1/3, and that is between negative 10 and 10. So we found the number that you had to plug in. So the actual algebra here is very easy. What I want you to understand is the idea behind it. That you have a starting y value, an ending y value, and it was continuous. So you went through every y value in between. Would you hit 17 somewhere between negative 10 and 10? What do you think, Caleb? Would you hit 17 somewhere on that interval?
Between negative 34 and 26.
Yeah.
You would.
Yeah, you'd hit 17 somewhere. Would you hit 25? Yep. Would you hit 27? No. You don't go to 27. If you want to go to 27, then your interval would probably have to go a little higher, maybe up to 11 or something. Okay? But this question wasn't about that. Okay. Any questions on that one? All right. So that one we're going to skip. And now we're going to look at the last topic in a second, which is end behavior. So end behavior is, I think, the easiest thing in this section to understand, even easier than the last two. So end behavior is when you look at what's happening to your function on the extreme left and right ends of it. You don't really care about all the twists and turns in the middle. You're looking at what's happening on the ends, like this. If I was going to describe the end behavior of that parabola, I would say it's heading up on the left, it's heading up on the right. This has exactly the same end behavior. It's heading up on the left, up on the right. It takes some little twists and turns, and you get some local mins and maxes in there, but that's not what end behavior cares about. It just cares about what's happening on the ends of the function. So let's take a look at this one. Y equals x cubed. Y equals x cubed. So if if you look at the end behavior of this one, what's happening on the left side? Yeah,
Pointing down.
down. Right side,
Pointing up.
up. The end behavior, one way to describe it, is like that. What's happening on the left side? Down. What's happening on the right side? Up. Okay, so that's one way to describe it. Here is another way. This is going to describe that. This is going to describe that. Right, so let me read this to you exactly the way you'd pronounce it, and then I'll simplify and explain it a little simpler. This says the limit of f of x as x approaches infinity. That's exactly how you read it. The limit of f of x as x approaches infinity. Now, f of x is a different way to describe what letter? Y. So what this is saying, limit means what's happening. What's happening to? Okay, so basically, what's happening to y as x heads towards infinity. Which way is infinity on the number line? Left or right? Emma? To the right. So this is saying what's happening to y as x heads to the right. Well, look at what you just wrote down. What's happening to your y value as you head further and further to the right? Yeah? And what is it increasing to? Infinity, yes. So what's happening to y as x value goes further and further right? The y value is going up and up and up and up to infinity, never stopping. Now the bottom one says, what's happening to the y value as x heads to the left? Negative infinity is to the left. So what's happening to my y value in this picture if I head further and further left? Yeah?
Approaching negative infinity.
It's heading down forever. And in math, we describe down forever as negative infinity. So this is two ways to write exactly the same thing. Okay? In calculus, you see more like this limit notation. That's what that's called. These arrows, it's just kind of a simple way for people to understand it when they're starting out. Okay, any question on that? Right. So there's 4 types of end behaviors. You can have down, up. What else do you think you can have besides down, up? Yep. Up, up. Yep. What else?
Down.
Down, down, and then up, down. Those are the four types. Okay, I can draw a quick sketch of all of them. So up, up is like your basic parabola. Down, down could be something like this. Doesn't matter if it twists and turns, it just matters what happens overall at the ends. Down, down. This one, that's a down, up. And that's an up, down. Every single polynomial will fit one of those 4 patterns. Now, what we want to be able to do is identify, just by looking at it, which one of the 4 it is. So we're going to practice that in a second. But let's do this. So let's graph just y equals x to the 4th. And we want to identify the end behavior. Okay, so I'm just going to change the 3 to a 4. What's the end behavior? Yeah, up, 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 up. It's one way to say it. Up on the left, up on the right. Now, if I wanted to describe it the other way, I could say the limit, or basically what's happening to y as x heads towards negative infinity. What's happening to y as you head to the left in that graph?
Yeah.
To what?
Infinity.
Infinity, yes. And I could say the same thing here. What's happening to y as x heads to the right? What's happening to my y value as x heads further and further to the right? To infinity. You don't have to use red and green boxes. I'm just doing that to very clearly explain which part of this these are describing. Any question on that? Does anyone think they know the pattern here of when you get like the same behavior on each end and when you get opposite behavior? Yep.
Even is the same, on is different.
Yeah. So this table summarizes basically if you have an even exponent, it's either going to both be up or both be down. How do you know which one? Well, you look at the number in front of the highest degree term, like this. If the number in front is positive and it's an even, that would fall in this category. Even, number in front is bigger than 0. If the number in front was less than 0, now it falls in this category, down, down. If your highest exponent is an odd, then you're going to have up, down, or down, up. You're going to have down, up if the number in front is a positive. Like, I did something like this. 8x cubed. Odd, positive. Right there. Odd, negative. Right there. So now you can figure out which way a graph is and behavior is going to go just by looking at those two things. Yeah. Any questions on that chart? So the leading term in the polynomial basically controls the whole thing. Right? So if I wrote something like 8x cubed minus 4x squared plus 3x minus 6, everything from here down doesn't matter at all. Does it change what the graph is going to look like a little bit? Yeah, it changes it a little bit. Changes like how it might twist and turn. But this is the only thing that affects end behavior. Just the term with the highest exponent. It controls everything. So, this term in front, we call that an EBM, end behavior model. This term alone predicts or models what that whole thing is going to look like, basically. All right? So what this is saying is you got some really long polynomial, and it's got all these different terms in it, just like I had up here. All the terms after the first one don't matter. The only one that's important is that one. And if you just write that one down, that is called the EBM, okay? End behavior model. Okay, so we're going to do, we have two problems. One, I'm going to give you an end behavior model. We're going to graph it, and we're going to see something. And then I'm going to give you a problem where you have to find the end behavior model yourself. Okay. Finding it is super easy. There's no math involved. Just write down the term with the highest exponent. The whole term. Coefficient, variable, and exponent. So we're going to start out with one where I'll give you the end behavior model. And I just want you to graph that and then the whole thing and see how similar or not they look. All right. So here's a formula.
Go back for like a quick second, please.
So I'm going to give you f of x, that'll be the original, and then g of x is the end behavior model. So actually, before I even show you, can someone tell me what the end behavior model is going to be? Zach? Yeah. So here's the original. Here's the EBM. They want us to graph it 2 times. First, graph it using those numbers, and then graph it using those other ones. Okay, remember, in order, x min, x max, y min, y max. Always. Okay, let's type this in. So we've got 2x cubed minus 7x squared minus 8x plus 16. And then 2x cubed. All right, they wanted, what did they say? Negative 8 to 8. 8 and negative 100 to 100. Okay, so here's your original. And here is your end behavior model. Do those look the same? Exactly. Not really. I mean, yeah, they both go down on the left, they both go up on the right, but they don't really look that close because you're zoomed in. The EBM isn't really meant to look the same when you zoom in. It's meant to look pretty close when you zoom out. Right? So now, let's zoom out. Right? I'm not going to change my graphs at all. I'm still going to graph the same 2 things. I'm just going to zoom way out. Negative 40 to 40. And negative 10,000 to 10,000. Now, there's the first one. That's the original. And there's my end behavior model. How do they look now? Pretty similar. I could probably zoom out even a little more and then it would look even more similar. Right? But that's the idea. These 2 things look exactly the same if you zoom out far enough. Okay? We know there's a lot of twists and turns happening in the middle because they didn't look the same when we zoomed in, but they do when we zoom out. Okay? So that's all I wanted you to see from that one. Okay, and the last one is to find the EBM and then tell me if it's up, 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 down, 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 up, up, whatever it is. Okay, what's the end behavior model for that formula? Okay, I want to know what's the expression that if I graphed it and I zoomed out enough, it would basically look the same as that.
Negative 1/2 x to the 4th.
So there's my EBM. And what's the behavior of that? Negative, even. Yeah? Down, down. Down, down. Okay. So any questions on that? Okay. So, test tomorrow. So I'm just going to list some things that you definitely want to know for the test. And then I'll give you the homework too. Okay, you want to know how to solve linear equations. I'll try to give you like a quick example. I'm not going to have enough time to do it out, but I'll just show you the kind of problem. 2/3 x minus 5x equals 12 plus 4x. You should be able to solve an equation like that. All right? Solve quadratic equations. There's 2 methods you can use. Factor quadratic formula. So that would be something like 3x squared plus 2x minus 6 equals 0. Now, don't actually try to solve that. I might have just made one up that's no solution. The one I give you on the test has a solution, but it'll look something like that. Okay? Solve inequalities. That would be something like negative 8x plus 6 is less than 4x plus 2. You should be able to solve that. What else do we do? Absolute value inequalities. So I'll just put including absolute value. That would be one like something like that. That's where you have to split it into two. Remember this symbol, what does that mean? Or. That symbol, and. You will come across that on the test. I know we've done a lot with the or symbol. I haven't done as much with and, but that's the and symbol. Solve quadratic inequalities. That's using a sign pattern or the calculator. But you've got to know how to solve a quadratic inequality. Domain and range. We kind of talk about that all year. Local mins and maxes. Okay, that's on the calculator. If you ask me tomorrow, I don't remember where it is. I'm not going to tell you it's under second calc. Okay, you have to know where that is. And you're going to have a short answer question having to do with something we did today, where you have to write like a sentence. So you should know how to describe the following. Continuity, what it means for something to be continuous, the intermediate value theorem, that's where I gave you the example with like the water, boiling it. It'll be one of those two. I'm going to ask you to describe something about it. Okay, but that's everything that's on the test.
Can I take a picture of that?
You can, it's kind of small, but actually I can make it a little bigger. It's going to be on YouTube too. And I'm going to give you the homework. I'll give you the homework right now.
Put it in your homework, so you check YouTube.
Well, I already wrote on the phone.
Okay, so homework tonight, it's on page 161. And it's those questions. Okay, so I will be here after school if you need extra help. Otherwise, we'll go over a little bit before the test tomorrow, but then I want to give you most of the time to take the test.